In this video, we're going to talk about proving triangles similar to each other and writing two-column statement reason charts. In the last weekly recap video, we talked about the three different ways of proving triangles similar. We talked about how there's SAS, SSS, and AA. Now, to show that sides are proportional in similar triangles, we often need to have side lengths in order to see if there is a common scale factor. In two-column statement reason chart proofs, since we often do not have side lengths, we usually have no numbers to work with in a two-column proof. Most of the time, it is going to be AA that we use to prove triangles similar. So in all of the examples that we do of two-column statement reason chart proofs, and when we need to prove triangles similar, we're going to look out for congruent angles and try to find AA. So in this example here, it says that SP is the altitude from S to NR. RT is the altitude from R to NS. Now, I know altitudes form 90-degree angles, so I know that SP is a perpendicular line since it's an altitude, and that means it makes a right angle right over here and right over here. The problem is, I don't know which of those two right angles is going to be important to me unless I first figure out which triangles I'm going to be focusing on in this diagram. I'm going to use the proof statement to try to figure out which two triangles I am proving similar. So according to my proof statement, it actually tells me that I'm proving triangle NRT similar to triangle NSP. So as you can see, this right angle is one of the three angles of this red triangle, whereas this right angle is not one of the three angles of either of the two right triangles. So this angle is going to be important to me because it's in one of the triangles that I'm proving similar to the other. Using that same idea, since RT is the altitude, it's once again perpendicular to the side of the triangle. So it creates right angles, and I'm going to be interested in this right angle because it's an angle of the blue triangle, triangle NRT. Now, notice how these triangles, the blue and the red one, are overlapping. So when we have overlapping triangles, there's always something that's shared, something in common, either a side or an angle. And here I see that angle N is what's going to be shared between the two triangles. They both contain angle N. And if you take a look at the letters of the names, you'll see that angle N is what's repeated in both of the triangle names. So we can say it's congruent to itself by the reflexive property. And now what we have is AA. We have two congruent pairs of angles, the right angles and the shared angle in the two triangles that we're proving similar. Give me a second. I'm going to write up the proof and pause the video so that way we can see what this looks like in a two-column statement reason chart. And here I have the full proof written up. Take a second, read through it, and make sure that you can match up everything in the proof to what was marked in the diagram. Notice how in my proof I did state first that I know that I have perpendicular lines. And the reason I know that is from the givens, we had altitudes, and I know that in altitudes are perpendicular lines. Sorry, that got jumbled up. Altitudes are perpendicular lines. Then, from knowing that I have altitudes, which are perpendicular lines, I concluded that we have right angles. That angle NPS and angle NTR are right angles. And the reason for that is perpendicular lines form right angles. So they're congruent to each other because all right angles are congruent. And then I mentioned the shared angle, angle N, that's the reflexive property. And finally, we're proving the triangle similar by AA. Okay, here's the next example. So here we have a trapezoid. And the only thing that we know about trapezoids is that there are one pair of parallel sides. And the sides that are parallel in the trapezoid are always the bases of the trapezoid. So I'm going to put that in. Looking at our proof statement, we want to prove that triangle BEC, I'm going to just highlight that triangle, is similar to triangle DEA. I'm going to highlight that triangle as well. Now, all of my givens are there for a reason. So I know that I have parallel lines. So I'm going to think parallel lines cut by a transversal. And if I highlight my parallel lines and my transversal, I see a letter Z. And that tells me that I have congruent alternate interior angles inside the lines on different sides of the transversal. Then, if you know this, I have intersecting lines here formed by the diagonals of this trapezoid, and I see that letter X. And whenever I have that letter X made by the intersecting lines, I have congruent vertical angles. Vertical angles are always congruent. And here in the two triangles, we have two congruent pairs of angles. So we have found our AA. We have the alternate interior angles and we have the vertical angles. I'm going to pause here and write up the proof. Please also pause the video and try to write it up yourself as well. Make sure everything from the plan gets into your proof. Here I have a 2-column statement reason chart for this proof written up. So notice that everything that we marked in the diagram is in the proof. Before we know that the alternate interior angles can be congruent, we do need to know that we have parallel lines cut by a transversal. So notice before I mentioned the alternate interior angles in my proof, I did state that BC is parallel to AD, and the reason bases of a trapezoid are parallel. Notice also I mentioned our vertical angles. Intersecting lines form congruent, I should say vertical angles, congruent vertical angles. And then we have the two triangles similar by AA. Okay, this one's a little bit more difficult. So if you take a look, we're actually going to be proving a proportion. And before we can prove a proportion, we first need to prove that triangles are similar. And then once we know triangles are similar, we know that their corresponding sides are proportional, so that allows us to set up a proportion. I'm going to use my proportion to figure out which triangles I'm focusing on. So AF is right over here, and DP is right over here. AC is attached to AF, so I'm going to use the same color for it. And that gives me two sides of a triangle. So I was able to identify one of the triangles I'm working with now. And the other segment's PB, and PB is attached to PB. So I'm going to put it in the same color. And now I can clearly see what the other triangle is that I'm focusing on. So I want to prove the blue triangle and the red triangle similar to each other. And I know in order to do that, I'm looking for two pairs of congruent angles for AA. Let's take a look at the givens and try to mark our diagram in order to figure out how we're going to get those congruent angles. So we have AB congruent to AC. So what that tells us is that triangle ABC has two congruent sides, or that it's isosceles. So I'm going to think about if I know my triangle has two congruent sides, that means it has two congruent angles. And according to the base angle theorem, those are the angles opposite on the congruent sides. That tells me that angle 1 is congruent to angle 2. And that's really helpful because angle 1 is one of the angles of the red triangle, and angle 2 is the corresponding angle to it in the blue triangle. So that gives us one pair of congruent corresponding angles already. So we're halfway there. We have one A, we just need another. Let's see if we can get it from the other givens. So we know that AF is perpendicular to BC. So here's AF, here's BC, they're perpendicular. That means they form right angles. So that means angle 5 over here is a right angle, and that's an angle in the blue triangle. Let's see if we can get another right angle in the red triangle. And luckily, our last given is talking about more perpendicular lines. PD is perpendicular to AB. So where they meet, a right angle is formed. Actually, two right angles, but we're interested in the one that's in the red triangle. And now we have two pairs of congruent corresponding angles in the blue and the red triangles. So we have after we prove the triangle similar using AA, it is one more step to prove the proportion that we're interested in. We're able to set up a proportion since similar triangles have proportional corresponding sides. So when we prove the proportion, after we prove the triangle similar, it's always going to be the same reason every time. And that reason is just what we just mentioned, that similar triangles have proportional corresponding sides. So I'm going to write that up in a proof. You might want to take a second and try to write the proof up as well. Pause the video. I'm going to pause as well. Take a second and pause the video and just go through the steps and make sure you can match up everything in the proof to what was marked in the diagram. To make it easier to follow, I just broke up the givens instead of putting them all in one step. I put the first given first, and then followed by the conclusion that we drew from it. Then I put the next two givens after that, followed by the conclusions that we drew from those two givens. And then finally, we proved the triangle similar using AA. And then it's one more step after using AA to prove a proportion. And the reason's the same every time. Similar triangles have proportional corresponding sides. Okay, now we're going to prove a product. So a product is one more step after proving a proportion. So same step so far, we're going to prove the triangle similar, then we're going to prove a proportion, and then after we prove a proportion, we can then prove a product. So from our givens, we know that W and CH are parallel. And my givens are there for a reason. So what I see is my parallel lines cut by a transversal, and I see that letter Z, which tells me I have congruent alternate interior angles. Inside the lines, different sides of the transversal. And I also see my intersecting lines that are mentioned in the givens. So I have congruent vertical angles formed by the intersecting lines. And there I have my triangle similar by AA. After we prove triangle similar by AA, it is one more step to prove a proportion. Now, when we're proving a product, we want to make sure that the proportion that we make cross multiplies to give us the product that we're actually trying to prove. And an easy way to create your proportion is to take the first term and divide it by the last term, so that would be WT over AT, and to take the first term here and divide it by the last term here. So the proportion would be WT over AT equals to HT over CT. And notice that when we cross multiply that, if we multiply this way, we get this half of the product that we want. And if we multiply this way, we get this half of the product that we want. So I'm going to pause the video and I'm going to write up this proof. Try your best to write it up as well. And then I will pause the video and show it to you. And what's very important when you're proving a product is to make sure that the proportion that you create does in fact cross multiply to give you the product you're actually trying to prove. So notice in my proof, I have my alternate interior angles being congruent due to the parallel lines cut by the transversal. I have my congruent vertical angles formed by the intersecting lines, so that gives me AA. Then it's one more step after proving the triangle similar to prove a proportion, and it's always the same reason every time. And then after that, it's one more step to prove a product. Now, the reason that we use to prove a product is always the same every time. When we cross multiply, these two terms, the ones in green here, are called the means, and these two terms, the one in red here, are called the extremes. So the way that we justify our cross multiplication is by saying in a proportion, the product of the means equals the product of the extremes. And it's the same reason anytime you want to prove a product. And here's the last example we're going to do for today. And once again, it involves proving a product. I recommend that you pause the video and you try your best to mark the diagram, draw it on your paper, and to try to come up with a plan for the proof and try to write up the proof yourself. Okay, so we have a parallelogram ACEG, and we're told that angle ABH is congruent to angle EFD. And we're proving that AB times FD is equal to HB times EF. So I see the two triangles that we're focusing on. And in this diagram, in fact, those were the only two triangles present. So I know my plan is going to be to prove these two triangles similar, then to prove a proportion, and finally I'll be able to prove the product that I want. So I already from the givens have one pair of congruent angles in the two triangles. Now I know that we have a parallelogram, so I'm going to think about my properties of parallelograms that involve angles. And the first one that comes to mind is that opposite angles of a parallelogram are congruent. So angle A and angle E are opposite angles of this parallelogram, so they are congruent. And that gives me my AA. After we prove the triangle similar, we do need to prove a proportion. Remember the trick, take the first part of the product, divide it by the last part of the product, take the first part of the product on the other side of the equal sign, and divide it by the last part of the product on the first side of the equal sign. And if we cross multiply, that does give me what I want here. And if I cross multiply this way, that does give me exactly what we want here. Pause the video and try to write up. And here is the proof completely written up. So notice how I mentioned how the opposite angles of the parallelogram are congruent. And that gives us our 8a, proving the triangle similar. Then after that, it's one more step to prove the proportion that we want. And it's the same reason every time. And after we prove the proportion, it is one more step to prove a product, and it's the same reason every time. It's the reason that justifies our cross multiplication. In a proportion, the product of the means equals the product of the extremes. Here I have a coordinate geometry proof, so I just want to show it to you quickly. So let's say we wanted to prove the big triangle here similar to the small triangle. Notice how the two triangles share an angle due to the reflexive property. Angle E is in both the small triangle and the big triangle at the same time. So the best and easiest way to go about this proof would probably be to show SAS. So in order to show SAS, you would need to find the scale factors of the corresponding sides, so of EF and EH, and of EG and EJ, and show that the factors of both pairs of corresponding sides are in fact the same. And then you'll know that the corresponding sides are proportional and the angle in between is congruent. So then you'll have SAS. A second approach is you can show that the segment is parallel to the base. That would just be two slope formulas, but I'm going to stick with SAS. I'm going to pause the video. I'm going to write it up. You should pause the video and try to do the distance formulas as well, and find the scale factors. And then I'll unpause the video so that way you can see the answer. Remember that coordinate proofs always end with a concluding statement summarizing what your calculations show. So my concluding statement is, since corresponding sides EF and EH are proportional by a scale factor of 2, and EG and its corresponding side EJ is also proportional by a scale factor of 2, and the angle in between the two proportional sides is congruent to itself by reflexive property, triangles EFG and EHJ are similar by SAS. Now I found that the corresponding sides were proportional because I used the distance formula to find the length of EH and its corresponding side EF, and then I divided side by big triangle over corresponding side from small triangle to get the scale factor. And I did that with EG and EJ as well. After I found the lengths, I did EJ, the side from big triangle, divided by the corresponding side to it from small triangle, and I got that it had the same scale factor. And just to recap on the steps for writing similar triangle proofs for two-column proofs like we talked about before in the video before the coordinate example, the steps are to prove the triangle similar, and remember that you might first have to figure out which triangles you're focusing on. If there's more than two triangles in the diagram, you can use either the proportion that you're trying to prove or the product that you're trying to prove in order to identify the triangles you're focusing on. Just like we did in the questions that we did together, you can use color and highlight the parts of the proportion or the product so you can see which two triangles they are parts of. After you prove the triangle similar that you're focusing on, you can prove a proportion involving the corresponding sides. That's one more step after proving the triangle similar. And as we talked about, it's the same reason every time. Similar triangles have proportional corresponding sides. And then finally, after proving a proportion, it's one more step to prove a product. And the reason's the same every time. In a proportion, the product of the means equals the product of the extremes.